let's have a refresher for the coming up test. Let's discuss equivalence relations. So let's see. So an equivalence relation is a binary relation R, subset of A cross A. A is a set with the following properties: reflexive X, R, X, for all X. So we have to understand that all these three formulas are universally quantified. So for every X, X are X. Now, second is symmetric. For every X and every Y, if X are Y, then Y are X. And thirdly, for every X, every Y, every Z, if X are Y and Y are Z, then X are Z. One easy, very easy example, even trivial example is equality. So this is example 1. X equals to X. For every X and Y, if X equals to Y, then Y equals to X. Then if X equals to Y and Y equals to Z, then X equals to Z. So equality is so clearly an equivalence relation. Let's do another example, example 2. This example will be so typical in the sense that every equivalence relation on a set A is of this type. So let's define example 2. So let A be a set and F be a function from A to another set B. So A is the domain, B is the some codomain. So the essential thing that a function F is domain A. So for such a function, let's define the relation on A like this. X related, so let's put this relation as R sub F, the binary relation corresponding to the function F. X R sub F Y is just F of X equals to F of Y. Okay, so how to prove that this is obvious, it's very simple to prove that this is an equivalent relation. So first, every element is related to itself. So what does it mean? F of X equals to F of X. How to check, that's how to check relatedness in this definition. So two elements are related if the function F takes the same value on those two elements. So the function F takes the same value on the same element X. F of X equals to F of X. For every X, so everything again is universally quantified. Symmetry. If F of X equals to F of Y, then obviously F of Y equals to F of X. To be read, if X are Fy, then Y are sub Fx. And thirdly, if F of X equals to F of Y, and F of Y equals to F of Z, then F of X equals to F of Z. Again, it's kind of very clear. So if X are Fy and Y are Fz, then X are Fz, so R sub F is transitive. So this function induces an equivalence relation on A, which we call R sub F. The equivalence relation induced by the function F. Okay. Example 3. So let's see another one. Example 3. So let's take a more concrete example. A equals to 1, 2, 3, 4, 5. And let's define X or Y, X related to Y, if X plus Y is even. Okay, so how to prove that this is an equivalent relation? It's very easy. X plus X is even. Then if X plus Y is even, then Y plus X is even because they are the same. And then finally, if X plus Y is even and Y plus Z is even, then x plus z is even. How do we prove this? Well, the proof is to write x plus z as a combination of those two. So, for example, x plus z equals to, if we add these two together, we get x plus y plus y plus z. These are both even. But then minus 2y is again even. But the simple fact is a multiple of 2. So x plus z is x plus y plus z minus 2y. That means if x are y and y are z, so if x plus y is even and y plus z is even, then x plus z is even plus even minus even is even. That proves transitivity. If x are y and y are z, then x are z. So that's an equivalence relation. So let's try to use our old conceptual diagrams for binary relations to see a picture of this equivalence relation. So again, A is a set 1, 2, 3, 4, 5, and then x are y if x plus y is even. So let's see the conceptual diagram. There's the set A, 1, 2, 3, 4, 5. Let's put some points here, 1, 2, 3, 4, 5. Okay, first of all, we have a loop at every point because it's reflexive. Okay, then 1 R3 and 3 R1 because of symmetry, 1 R5 and 5 R1 because of symmetry, and finally 3 R5 and 5 R3 back and forth because of the symmetry. And then 2 R4 and 4 R2, right? So what do we notice here? We notice an interesting thing. So this set A splits into two subsets. So one subset is so clearly visible that the set within the set 1, 3, and 5, we have a total relation. Everything is related to everything. So A can be written as a union of the subset 1, 3, 5. All elements in there are related. So the total relation of, let's call this block 1. It will be a block of what we'll be calling a partition. Within this block 1, everything related to everything. Like we see here, 1 is 1, 5 is 5, 3 is 3, and 1, 3, 5 back and forth with each other. Union, the second block will be 2 and 4. So within this block 2 and 4, 2 is 4, 4 is 2, 2 is 2, 4 is 4, everything with everything. So within a block, we have a total relation. Total relation in the sense of everything being related to everything, including itself. Right? Now, between different blocks, no relations at all. So between different blocks, we have no relations. So what we got here is a partition. So a set A, the set A, so once we have an equivalence relation on A, the set A splits into a disjoint union of blocks. That's called a partition. So let's discuss partitions. That's a partition of A. It's a way of writing, so we have formal definition of union of blocks, B sub I, right? Then, B sub I are non-empty. And the third axiom of partitions is B sub I, the block I intersect with block J is empty as long as, so if I not equal to J. That's a definition of partitions. So what we got here is whenever we have an equivalence relation of A, we've seen this through an example, the set splits into a disjoint union of non-empty blocks. So this would be block 1, block 2 in this case. In general, every equivalence relation on a set A induces a partition of A. Right? So we have very important theorem as between equivalence relation on A. So equivalence relations on A, they're basically the same thing as the partitions of A. So they are to be identified with each other. Every equivalence relation induces a partition, and for every partition, okay, so how to go from partitions to equivalence relation. A partition of A, like I said here, disjoint union of blocks. Blocks are non-empty. Two different blocks do not intersect. Different blocks do not intersect. So it's like we have a continent split into countries. Every country says something in it, so non-empty, and they don't intersect. So we have partition of the continent. So we have a chart in this case, so we have partition of A. We can say block 1, block 2, and so on. Right, so if we have a partition, how to define an equivalence relation? Let's how to go from partitions to equivalence relations. So let's see, X related to Y if X and Y belong to the same block. If there exists an I such that X and Y both belong to block I, the same block. So two elements are related if we have a partition like this, if X and Y belong to the same block. So this offers a nice vision of the equivalence relations, right? And then from equivalence relations to partitions, we can understand intuitively in the same way when we went from the binary relation on 1, 2, 3, 4, 5, X, R, Y, if X plus Y is given. But in general, we can put up a more formal representation. If R is equivalence relation on A, then the partition is A is the union over all elements X in A of the blocks of X. So if X is an element of the set A, then the set full set A. The block of X is all the elements related to X. So the block of X is the set of all Y in A with the property that Y related to X. So there's the block of the partition containing X. Okay, so let's develop some ideas here. How to prove, for example, that the block is non-empty. Every block of the partition is non-empty. Because it contains at least X. So because X belongs to the block of X. Now, with respect of blocks being equal or disjoint, we have two choices here. If X are Y, then the block of X equals to the block of Y. So if X and Y are related, then their blocks are the same. So they belong to the same block, like shown in this picture before, which I just erased. So let's see. So let X are Y. How to prove that? Show that, how to show that the block of X equals to the block of Y. So simply we show an equality by letting an element belonging to the left-hand side and proving as the right-hand side, and similarly letting an element belonging to the right-hand side proving as the left-hand side. So we assume that X are Y, so let T belongs to the left-hand side, the block of X. How to translate this? That means T related to X, because that's the definition of the block of X, all elements related to X. So T are X. But from T are X and X are Y, because we started with X are Y, so from these two, we get T are Y. So we started to, so that means i.e. T belongs to the block of Y. So we started with let T belongs to the block of X. We prove that T belongs to the block of Y. And because the situation is logically symmetrical, we show that the block of X is the same as the block of Y, given that X is related to Y. What happens if they are not related? What if X is not related to deny, not related to Y? Then the block of X and block of Y do not intersect. Then the block of X intersection with the block of Y equals to empty. How to prove this? Prove by contradiction. Let's assume that block of X intersected with block of Y is empty. So say block of X intersected with the block of Y is non-empty. Being non-empty, there is something in it. So let T belonging to block of X intersected with block of Y. Right? Then what does it mean? X is related to T. Actually, so T are X because of the symmetry, we can say X are T, and T are Y. So X are T because T belongs to block of X, and T are Y because T belongs to block of Y. From these two, by transitivity, this would imply that X are Y, which is a contradiction because we started with assumption if X not equal to Y, is not related to Y. So if X not related to Y, the blocks of X and Y do not intersect. So this kind of everything converges to the picture of a partition of A. So this is exactly a partition. A is the union over the all elements, and I put it like a small italics, like small elements X in A, the block of X. The block of X consisting of all elements of A which are related to X. Good. Now, let's go back to the first example where we prove that for every function defined on A, we can construct an equivalence relation R sub F correspond to the function F. So now let's prove that every equivalence relation on A is of the form R sub F for some function defined on A. So for some function from A to some codomain B to be determined. So what's the proof of this? So let's start with let R be subset of A cross A be an equivalence relation. We have shown that this equivalence relation induces a partition. So let's consider partition corresponding to this equivalence relation. So the partition will be A will be union of an X belonging to A of the block of X. Block of X consisting of all elements related to X. And then the set B will be the set of all blocks, where X belongs to A. We know that the set does not allow for a repetition of elements. So we only repeat the block once in the set. So the set of all possible blocks in A. So then we define clearly a function from A to B. F of X is the block of X. So basically, the function is defined in a very canonical way. The value of the function x is the block of the partition corresponding to x. So let's give a more concrete example of this theoretical construct. So in the previous example, consider A will be 1, 2, 3, 4, 5. And then we've seen that x are y. If x plus y is even, is an equivalence relation on A. So let's see. So what would be f in this case? What will be f? So that r equals to r sub f. So that r equals to r sub f. So the codomain of this f will be the set of blocks. So let's see. The A was we've seen that the blocks of A were 1, 3, and 5. So within a block, everything is related to everything. Between two different blocks, there are no relations. So let's call this block 1. Let's call this block 2. Block 2. So the set of all blocks where x is in A. So that's a set of all blocks. Set of all blocks, or as in equivalence classes, is simply B1 and B2. So a set of two elements which we'll call B1 and B2. So how do we find the function? So here is the set 1, 2, 3, 4, 5. That's A. And B will be considering B1 and B2. I have two elements, B1. One is named B1, another one is named B2. Now, for every element among 1, 2, 3, 4, 5, the function transforms this element, goes from that element to the block in which it belongs. So 1 belongs to block 1. Right? That's block 1. 3 belongs to block 1. 5 belongs to block 1. 2 belongs to block 2. And 4 belongs to block 2. So that's the function from A to B. And the equivalence relation induced by this function is exactly the same with the equivalence relation which we started with. So x are y if x plus y is even. For example, look at 1 and 3. 1 and 3 are equivalent according to RF because f of 1 equals to f of 3. But according to R, 1 and 3 are equivalent because 1 plus 3 is even. So R is the same with R sub f.